power is very important to National Grid. It is a growing source of energy. We receive very detailed weather forecasts for the locations of the major wind farms. And we feed that into our computers, and a forecast for wind speed turns into a forecast for wind power. And that's then used to know whether greater reserves are needed so that more power can be called upon at short notice. Holding reserves costs the electricity consumer and the industry more money. The forecasts that we receive at the moment are very good, but they have a certain amount of error in them. And we want to minimise that error even more if we possibly can. It made a lot of sense to approach the meteorological department at Reading University, where they have worldwide expertise in weather forecasting, and we wanted to know if there was anything new that we could do to improve our systems.
Weather is incredibly complex, and so to forecast it, you need to gather as much data as you possibly can from a range of different sources. So from radar, satellite, just observations near the ground, and then assimilate all of this data into a model, and then run this model to see what will happen going into the future.
My research in particular is focused on extreme wind power events and also how predictable they are. Looking back over 34 years, we get a huge range of different weather scenarios, and we sort of try and infer from the wind speeds what would have happened given the present distribution of wind farms. This plot shows an example of the kind of statistics that we've produced in this project. We can ask the question, how long was the longest low wind period over the last 33 years? And from this type of graph we can read off, say, for example, that the power dropped below 10% of its highest possible value for a period of 12 days. This is really important for National Grid to know, because if the wind speed drops below a certain amount, then that power has to be sourced from elsewhere on the grid, and that shortfall has to be made up.
We've looked at a number of different offshore wind farms, so we're trying to set up a model which looks at how the wind speed varies across the farm for different wind conditions. Here we have some results from the model, and this is for a large offshore wind farm, and we're looking at the reduction in wind speed as you propagate through the farm. And you can see a 20% reduction in the wind speed between the leading edge and the downstream edge. The model's set up now, so we can run it for any wind farm we want, and we can therefore see what the power characteristics of that wind farm might look like. I particularly like the relevance of our research and how we can actually see it being used in operation at National Grid.
It's very motivating for the researchers. So working with industry and understanding what the real network challenges are, that then helps us build better models, run better science that's got real impact.
The more renewable energy that we have installed on the National Grid, the more uncertainty that brings us. And if we can manage that uncertainty and reduce it with accurate forecasts, then we can reduce our reserves and save money and run the system more economically and more securely.